I'm now going to summarize what we've talked about in terms of projectile motion, and the summary will have 3 parts. So the first part is to just focus on the model itself. So when we're using the projectile motion model, we're thinking only about gravity. That is the only acceleration we need to worry about, and as you will soon learn, when we're talking about accelerations, we can think about forces, and so gravity is the only force we need to worry about. You need to consider that this is our object is going to be treated as a particle. We don't care about its size or shape. And its initial velocity, we're going to say, has a speed v0 and an angle theta. And again, keep in mind that you can't necessarily just relate that to a position in a triangle. In the x direction, you have uniform motion. And in the y direction, you have constant acceleration. So you don't have any acceleration in the x direction, and in the y direction, you have negative g. Delta t, so time, is what ties together what's happening. That as we imagine our particle marching along this trajectory, the relationship between x and y is given by time that you don't necessarily see. You can't use this model if there is significant air resistance. You would need to think about a different way of approaching the problem. So keep in mind that you can't use this every single time, but in general, once we introduce air resistance, it's a much harder problem, and we'll need forces to think about that. So how do we actually go about solving a problem that relates to projectile motion? Again, it's important to have a strategy. So the first step is to think about your model, because when I give you a problem, I'm probably not going to tell you, hey, use projectile motion for this. So the first thing to think about is that, is it reasonable to ignore air resistance? If it's a person hanging from a parachute, probably not. For most other situations, sure. So if you can ignore air resistance and it's a 2-dimensional motion, you want to use projectile motion. If you can simplify it down to 1 dimension, i.e. just up and down, then you don't need to use projectile motion. You can use free fall. It's a 1-dimensional problem. So if you can ignore air resistance and it's 2D, then this is a good model to use. So then you want to visualize, and this is really important. Draw a picture. Think through what your initial height is and your final height. So you're sketching out the trajectory in that case, but make sure that you're not oversimplifying. So be very careful, draw your initial and your final position, think about what you know that's tying it together, and define symbols. And please be careful about this. There's a lot of variables to use here. It's really helpful to write those out at the beginning to, for instance, remember that acceleration in the x direction is 0. So then we want to start solving, and we're going to start with those 2-dimensional constant acceleration kinematics equations. In the y direction, you're going to plug in negative g for acceleration, and in the x direction, you can actually use uniform motion because acceleration is equal to 0. So you're going to be starting with these equations, but you need to go back to your representation, your picture, to understand what you do know, what you don't know, and what you're plugging in. You might, for instance, need to be using the highest point and the fact that at the highest point your final velocity is going to be equal to 0. You might be asked about when it hits the ground, and again, in that case, you're using this position. So usually you'll have enough information to solve either in x or in y. Find delta t and plug that in for the other. So you're frequently going to need 2 or 3 equations from this. So at the very end, look at your answer. Does it make sense? Is that a reasonable distance for that object to go in that scenario? Or is that a reasonable height? Is that a reasonable amount of time in the air? My goal is to always give you reasonable problems. The book does as well. So if you get an answer that, your car going off the cliff went 3,000 miles, you probably want to back up and ask and look at what happened. So finally, to just really stress the most important aspects of projectile motion, projectile motion is what we have when we have an object that is only being acted on by the force of gravity. That means air resistance is negligible. And again, it's the 2-dimensional scenario that corresponds to free fall. We get to treat x and y motion as independent. The only thing tying them together is time. If you have a position equation that's involving both x and y components, you've probably done something wrong. In the case of working in x, you actually have a uniform motion. That's the correct model to use. And in y, you want to use constant acceleration, with your y component of acceleration being equal to negative g. Again, be very careful about your signs in y, both for the acceleration itself and for changes in position. Finally, make sure that you do not oversimplify. Projectile motion involves a fairly complicated trajectory. We frequently get to simplify that, but don't assume simplifications that aren't valid for whatever situation you're trying to find a result for. So for instance, the initial angle is probably given in the problem, or you might need to calculate it based on other information given. But never construct a right triangle based on positions and use that for projectile motion. That's never correct. Make sure that you don't assume level ground if that's not the situation you have. Your starting and your final height might be the same, but if, for instance, an object's being thrown off the roof or to a roof or off a cliff, that's not the case, so be careful about that. And if you're looking at an object colliding, for instance, going in the window of the math office, make sure that you're not assuming that that's occurring at the top of the trajectory unless you've been told explicitly that it is.